Hello, this is a note on a celestial navigation exercise, finding your latitude at noon. The most famous exercise in celestial navigation. It's using a sextant and the peak height of the sun at midday, and from that determining your latitude. And we're doing this as an exercise in one of our quizzes, quiz 3 in our course, quiz 3 number 18. And here's the problem. I'll come back to it, but before I forget it, I want to draw everybody's attention, the students that are looking at this, special instructions for this quiz. You need to download these full set of the increments and corrections. That's a set of tables that we need, because in our textbook, which I'll show you in a moment, where all the other data is located, we only have a handful of these special increments tables, and you need some that are not there, one that's not there. So you just go to that link that's provided here, and you'll see a set of these, and we're going to want 42 minutes. Our own table has about like 8 pages, but not this one. Okay, so there's the question we're doing, number 18, and all this is totally standard. And actually, the video that I just did happened to be the one where we predicted the time. We predicted the time that this would take place, and that all looks fairly consistent. Actually, it looks like 11:42. So here's the date, July 25th, 1978. Kind of dates are, well, I don't know if it dates it. I mean, it certainly shows when we started teaching celestial navigation, because this is an example from our textbook. But we also have new dates, and the textbook's been reprinted and updated many times. But the beauty of celestial navigation, that could be 1878 or 1778. It wouldn't really matter. What we're doing here hasn't really changed that much. So here's the exercise, July 25th, 1978. This is a watch time and a position. Normally you start there and you'd have a course and speed, and then you DR off to some place where you actually did the sights. But in this case it says you are becalmed, boat speed is 0. So that's where we're sitting, and what's important here for this exercise, we really need to know what our DR latitude is, 4217. When we predicted the time in the last video, we needed to know what our DR longitude was. Now we don't really care what that is at all. We care about what our DR latitude is, just as a reference point as we work through this. So we take a series of sights, and we get the peak height of the sun, and the peak height of the sun. Then this is the index correction, how the mirrors were lined up, and that was measured with a horizon or some way, and we got 1.1 minutes on the scale, on the arc, on the scale. The height of our eye above the water, 9 feet, and the peak height of the sextant was at 6721.9. Watch is set to zone 3, zone plus 3, and the watch air is 4 seconds fast. Now that actually that still doesn't matter much here, but anyway, we've got that information. This noon sight, we could be wrong on our time by a minute or two. It wouldn't make much difference, hardly at all, on this site. That's why one of the reasons this type of site is popular, because it's very forgiving. Very forgiving. You have quite a period of time to measure this number. You're not going to just miss it. You got a few minutes to catch it and be pretty close, and so forth. Okay, so what is your latitude? That's what the question is. Now let's see where I start. Let me just remind. Let me just do a reminder here from what we did last time. Last time we predicted the time. We predicted the time that it was going to happen, and the GHA of the sun is tracking along this way, right? Tracking along like this, and when it's due, and this is the zenith distance. That's the height of the sun. And let's see, do I have another picture here? I thought I did. Yeah, here's a definition of this comes into play in what we're doing. Here's just a definition of these angles. Here's a HO, or something. You measure this with a sextant from the horizon up to the star or sun. from the horizon up to here. That's called H, or in this case it says HO, but it's some sextant height, and this is with corrections. And then the distance from here down is called the zenith distance, and these two sum to 90 degrees. So if we if we measure H, we find Z by 90 degrees minus HO. Then we're not getting into that at this point, but Z is really the fundamental value we care about. How far we, where we are relative to the point overhead, but we can't measure that directly. So we measure H and then find Z. So there's the two angles there. So here is Z, which is the reason this has a physical importance is because that is the distance to the GP, and then this sun's tracking along here, and you see the Z gets smaller as it goes along. This distance to the GP gets smaller, and as it gets smaller, you see as Z gets smaller, H gets bigger. I mean, this Z minus 9, that gets smaller, that's fixed, so H gets bigger. So as this is marching along here, the sun goes up. So that's why, in a sense, as the sun circles the earth like this on a fixed latitude equal to its declination, we perceive it as rising in the sky, peaking out when it goes by us, and then fall down. And that's a noon sight. And the nice part about this sight is if we measure this height right here, we can figure our latitude, and we very simply, just some arithmetic. Okay. So that's that, and there's that. So let's get started on the process, and let's see, how do I want to start? Well, let me, no, that would not be the first one. I made these notes here. Okay. So what did they tell us here in the problem? The problem tells us that the peak height was at 11:42:23. So it's going up and up like this and then down, right? So this is 11 hours, 42 minutes, 23 seconds watch time. And then we have our watch is 4 seconds fast. So we have to subtract that. And then we have to add 3 hours to get to the GMT. And so here's the time. Here's a UTC of the site. 14 hours, 42 minutes, 19 seconds. And that's what we go in the almanac for, to find the declination. And the declination is just the latitude where the sun is tracking along here, like this. It's going along like that, and that's on a railroad track up there, locked in, and that's locked in at a latitude equal to declination of the sun. And throughout the year, that varies. Throughout the tropics, it goes all the way up to the edge of the tropics, then down across zero, down the bottom tropics in here. But looks like that. Okay, so now we've got the time. That's the time. So now we want to find out what's the declination at that time, and then we go in the almanac. So here then, let me move some of this out of the way. And here is our book. In the back of the book, we have the altitude correction tables. No, we want to go to the daily tables. These are called the daily pages of the Nautical Almanac. This particular problem, these T2 up here, T2, T3, that's our in-house notation we use in the textbook, just for quick reference. Easier to say. And so this is the page we want, July 25th. We want the sun. We want date on the sun. And then we come down here, there's 3 pages on the day. We want the middle day. And here's 25th. We want here 14 hours, 42 minutes. So here we got 14 hours, and then you go straight across here. You see there's no degrees part. I have to go upstairs to get it. The minutes are 39.3. Then I have to go upstairs to the first one that's written. And that's north, 19 degrees, 39.3. That's the declination of the sun at 14 hours even. So I write that down on a piece of paper. Okay, 39. Now I'm going to have to go in and figure out some correction for this 42 minutes. And the way you do that is, first of all, we want to see, is it getting bigger or smaller with time? So we just look at this declination. Here's 39, 38, 37, 37, 36. So the declination is getting smaller. And the reason it's getting smaller is we're July, and at June 21st is when it was up at its peak excursion north at 23.5 degrees or so declination. And now it's starting down. So it's starting down. So the declination is decreasing. Then we go to the bottom of the page. And the bottom of the page tells us the so-called D value. And the D value is 0.5, but we now know the sign. We have to figure that sign by ourselves. This declination is going down, so we write that down in our piece of paper as minus 0.5. So here I've got the declination 14 hours is 19 degrees, 39.3. The D is minus 0.5, and we determined this not in the tables, we determined this ourselves by inspection. Now we have to find that correction, and that's where we need that special increments and corrections table. Let's see, do I have it here? Oh yeah, okay, I have a section of it. I just have a section of it right here. That's 42 minutes. And now keep in mind, let me just see the I just want to show you what a whole one of these looks like. Arc to time. Well, actually, it's right here. Let me move this aside. So there's a full page of what these look like. There's actually 2 minutes for each page. And then there's all this, and it goes from 42 minutes, and there's seconds down the side. But that's used for the GHA, not the declination. The declination, we only, for the sun we're dealing with now, only ever uses just this little corner of the page. The D value is never bigger than 1. So when we come back over here, to the page that we had to look up, we want to know what is the correction. In other words, if this is not fancy here. This just says that at 14 hours, the declination was north 19 degrees, 39.3. And then at 15 hours, it was north 19, 38.7. It's gone down that much, which is usually, something like 0.5, and that looks like it was 7 from 13 is 6.6. But throughout the day, the average was 0.5. So all this table is doing is what's very famous in celestial navigation. We don't ever have to multiply. Lord knows we never divide. We never divide in anything. But we don't even have to multiply. So this interpolation, just trying to find out, it's north 19, 39.8, and then down here it's 39.3 when you go all the way to 14 hours. The question is, what is it at 14 hours 42 minutes? And the answer is it's dropped 0.4. It's dropped 0.4. So we come over here, we take 39.3 minus 0.4. There's the declination of the sun at 14 degrees 42 19. And basically, for doing these declination, the latitude at noon problems, you don't really care about these seconds at all. You can round that to the nearest one. So less than 30, we rounded it down to 42. So now I have the declination. That's one of the components that we need. We've looked up the declination. We could do this 20 times in the time I've been here sitting talking about it. It's that quick. All right, now what we need is we need to come back and find out what the zenith distance is. What the zenith distance is, the Z value. Because the answer of the way this, I'm not doing a theory on the noon site here. We're just working one. But I'll tell you the punchline that here's the declination. Now we're going to find this zenith distance, which is 90 minus the corrected section height. And then once we have the zenith distance and the declination, the latitude is either the sum of those two or the difference between those two. And then we always can tell which is which by we look at the DR. The DR is 4217. Oh, I wrote it here. DR is 4217. So this is all real simple. I mean, once we had these numbers. So we did one thing that involves some table lookups. Now we just do some corrections here. And this is standard. This correction, HS going to HO, is the same for every site in celestial navigation. Sun, moon, stars, or planets. Every time you have to convert HS to HO, making essentially the same corrections. First, there's index. Okay, that's the HS. This is a number read right from your sextant. No corrections, no nothing. 21.9 minutes. And so the index correction is what you measured to get the mirrors properly aligned. You measured that with the horizon. Again, this is not a topic of that. We're not covering that here, but here it's the IC. Oh, but we are covering this. Let's see what the problem states. The way this is taught in celestial navigation around the world, I hope, is we don't say the index correction is plus or minus. We say it's either on the scale, or it says arc here, but on the scale or off the scale. And then we have a jingle. If it's on the scale, you take it off. If it's off the scale, you put it on. So this one is on the scale, so we take it off. It's -1. Then the dip is always minus. That is seeing over the horizon a little bit because we're at an elevated height. In our case, our height was 9 feet. So I have to go in here to the altitude correction table. Let's see, did I make a link to that? Altitude correction, dip and altitude correction. Yeah, okay. So it's a page in the Nautical Almanac, and so we go in here. What is this? Altitude correction dip. Oh, you know what? Okay, so there's what the full table looks like, and I think I just remembered. I made a copy of it here. Let me just get rid of this. I made a copy of that page here. So what do we want here? Okay, look, we're going for we need the dip. We need the dip. How much are we seeing over the horizon? And the dip table is right here. And this column is feet. This column is meters. So, and our feet is 9 feet. We're 9 feet above the water. So anything between 8.6 feet and 9.2 feet, that's -2.9. And so that is the dip, -2.9. So we take away the HS, we take away the IC, we take away the dip, we get HA. This is called sextant height. This is called apparent height or apparent altitude. You see, everybody, you can have 10 people, 10 people on different decks on a ship, and all of them are going to have different sextants, so they're all going to have a different index correction. Then they're all on different heights, and they're all on different heights on the ship, maybe 30, 40 feet different from each other. So you ask them what that number is when they measure it, they're all going to be different. Every single one's going to be different. But now, after you make this correction, everybody on that ship with 10 different kinds of sextants and 10 different elevations above the water, they all should come up with this number, 67 degrees, 18.0. That's called the apparent height. Now, it's still just apparent because the light rays bend a little bit coming in, and also we're measuring the bottom edge of the sun, the lower limb. Let's see. Double check always lower limb. Lower limb of the sun. And so we have to do a correction to get to the center of the sun. All the calculations in celestial navigation relate to the centers of the celestial bodies. So now we have to do the altitude correction. And so that's done on the same table. It's altitude correction. It goes 10 to 90. Then there's one more page that goes 0 to 10. And that 0 to 10 fills up the whole page. And that's because at these low angles, these numbers change very quickly because the refraction of the light's changing very quickly, how much it bends. But here we got this one. So here now, though, is something important to know. We've got to know we're in July. There's 2 columns here. There are 2 columns. And there's a lower limb and upper limb. See, the lower limb, you're adding about half the size of the sun, half the semi-diameter, as plus 15.6. But if you measured the top edge of the sun, then you subtract something. So we're adding because it's a lower limb. But we want to be sure we're in the right date. Because as the Earth's orbit is not a circle. The Earth's orbit is a slightly elliptical. And then, so one time of the year it's a little closer than the other time. And so the apparent size that we're correcting for changes slightly. It's a very sensitive business. All these things are very sensitive. Okay, so here's what you do. And you go into this with nominally out. That's apparent altitude, apparent height. And we've got, what do we have? 67, 18.0. So you go down, everything, oh, look at that. It's barely there. Well, it doesn't matter. Anywhere between 67.17 and 73.16 Can I make that any bigger? I don't know. Well, I don't think so. No. Okay. Anyway, I don't. Oh, maybe that's not even in the view. Hang on just a minute. I didn't realize what I was doing here. Okay. There we go. That's a little better. So anything between 67.17 and 73.16 has a altitude correction of plus 15.6. So that's that. And so we come over here now, altitude correction plus 15.6. So we take this plus this number plus this number. There's the HO. That's corrected, all the corrections out of there. Now we find the zenith distance, 90 minus HO. We rewrite this 90 as 89 degrees 60. See, that's the same as 90, 60 minutes per 1 degree. Then we subtract this number from that, and we get the zenith distance, 22 degrees, 26.4 minutes. And we got down the other page, the declination was 1938.9. Now we have to ask ourselves, now again, there are rules, there are formal rules. You can make a table, you can make notes in your almanac, you can do anything in the world to get the official rules for do you add or subtract. Do you add or subtract? There are rules for that. But really, it's rare in life you're going to need a rule. What you do is you look, if I add them, and I get nonsense, then I subtract them. So look, case, if I add these two, that's 22 and 19, that's about like 41 or something. And sure enough, what's my DR? 42. So it's obviously you're adding them. If I subtracted them, that puts me right down by the equator. You know, see, it's totally wrong. So we know we add them. So I add those two together. Oh, why did I? Oh, and then that's my DR. So we add those two. So the latitude sum or difference of zenith distance and declination. And so equal. So in our case, it's a sum. And we just do that. We take 1938.9 plus this. And you get 41 degrees, 65.3 minutes. Right? I just add them up, minutes and then degrees, and then I take this 60 out of here and put it over here. That's 42 degrees, 5.3. And that is a noon sight. That's how you find latitude. Again, you could do this from beginning to end 10 or 15 times once you've done one or two. You could do this 10 or 15 times in the time I'm here talking about it. That's the end of that video.